Welcome to my talk on ranking structured objects with graph neural networks. My name is Clemens Damke and this is a joint work with Eike Hüllermeier. Let's start off by looking at what structured object ranking actually is and what it might be useful for. As input, we assume that we are given a number of ranked structured objects, for example, a ranking of molecular graphs, which we can also interpret as a partial observation of some underlying preference relation. Our goal is to generalize this preference relation by training a model which is able to rank previously unseen graphs. For molecular data, as shown here in these problems, applications can be found, for example, in biology, where there's the so-called protein docking problem. In medicine, there's the so-called drug screening problem, where one wants to find promising active ingredients that will have a certain desired effect. However, apart from molecular data, there are also interesting applications, for example, looking at social networks, where one problem might be to find a well-working organizational hierarchy. Another application for ranking structured objects might be in the domain of planning, where a ranking model might be used, for example, to suggest a schedule to the organizer of an event. Now, what we propose is that all these types of problems can be tackled by what we call the RankGNN architecture. At a high level, the architecture consists of two modules. First, a graph neural network module, which takes in as input a number of graphs and embeds these graphs into some vector space. Secondly, a neural ranking model, which takes these graph embeddings and produces a ranking of our input graphs. Since I won't assume that everybody is already well familiar with how graph neural networks and neural ranking models work, I'll now give a brief introduction to both modules, starting off with the graph neural network module. As just mentioned, a graph neural network takes a graph as input, where the common assumption is that we assign to each vertex vi some feature vector xi. Depending on the type of graph neural network, there are also architectures that take in edge feature vectors as well. Now, similarly to how a CNN applies a number of convolutions to an image, a GNN applies a number of so-called graph convolutions to a graph to produce a convolved graph representation. After applying the convolutional layers, we get a convolved feature vector for each of our vertices. To produce a final graph embedding from these feature vectors, one then applies a pooling layer, which combines all vertex feature vectors into a single graph embedding vector. The pooling layer itself is typically fairly simple. Often a simple sum or mean operator is used. Generally speaking, the convolution layers are probably the most interesting part of a graph neural network. Graph convolution layers can be roughly classified into two families, spectral and spatial convolutions. Let's start off by taking a closer look at spectral convolutions. The core idea behind spectral convolutions is to interpret the vertex feature vectors as a multivariate signal in the space that is described by our input graph. Using the so-called graph Fourier transform, we can translate this spatial graph signal into a spectral representation of that same signal. Now, to perform the graph convolution operator, we can make use of the convolution theorem, which states that a convolution in the spatial domain is equivalent to a pointwise multiplication in the spectral domain. This means that we can perform a convolution on our original signal by multiplying the spectral representation of it with some learned filter function. For example, such a bandpass filter might filter out the low and high frequency components of our spectral representation. By then applying the inverse graph Fourier transform, we can translate our filtered spectral signal back into a spatial signal. With this approach, the learning problem essentially boils down to tuning the shape of this spectral filter function. The advantage of this convolution approach is that it is fairly expressive, by which I mean that it is able to capture a large variety of structural graph features. However, this comes with the downside that it is fairly computationally expensive. In the worst case, where we consider learned filters with an arbitrary shape, we would in fact have to compute an eigenvalue decomposition of our graph Laplacian matrix in order to apply a spectral filter. Luckily, there are ways to get around that, for example by restricting the learned filters to the class of Chebyshev polynomials, but even then, computational cost still remains an issue. Partially due to this reason, attention has recently started to shift more towards spatial convolutions. Conceptually, this type of convolution is actually a lot simpler than the spectral approach. There, we perform the convolution directly in the spatial domain by using a neighborhood aggregation scheme, which looks as follows. In each convolution, we combine the current feature vector of a vertex with the feature vectors of its direct neighbors using some aggregation function. Depending on the type of convolution layer, this aggregation function might be a simple mean operator. Other architectures use something like a sum, and there is also a huge variety of other types of aggregations, which I will not go into now. One interesting side remark relating spectral and spatial convolutions is that we can actually interpret this type of neighborhood aggregation as a very restricted type of spectral convolutions, namely one where the learned filter function is restricted to the class of linear functions. This simplification has two main consequences. Firstly, it allows us to perform convolution much more efficiently than would be possible in the general spectral setting with arbitrary learned filter functions. More specifically, the runtime of a spatial convolution approach as described here is linear in the number of edges, which allows us to make use of commonly made sparsity assumptions. The main downside of this spatial convolution scheme is its expressivity. More precisely, it has been shown that it is limited by the so-called one-dimensional Weisfeiler-Lehmann graph isomorphism test. One well-known practical consequence of this limitation is that this type of spatial convolution is unable to account for the presence or absence of cycles in a graph. This can be seen here in this example, where these two clearly non-isomorphic graphs would, to this spatial convolution operator at least, look completely identical, forcing it to map them both to the same graph embedding vector. To overcome this limitation of the simple neighborhood aggregation scheme, recently a number of so-called higher order convolution operators have been proposed. For example, the 2WL-GNN architecture based on the two-dimensional Weisfeiler-Lehmann test, as the name suggests, which we have recently proposed, or the so-called K-order networks, or the so-called graph substructure networks. The details of how these higher order spatial graph convolutions work will not be discussed here. Instead, we are now going to go back to the RankGNN architecture overview. We just saw how graph neural networks make use of the structural information of graphs to produce a graph vector embedding. In the next step, we are going to look at how neural ranking models are able to produce a graph ranking from these graph vector embeddings. Generally speaking, neural ranking models can be classified into three families. The first one being that of pointwise ranking models. Pointwise ranking models are trained with numerical target utilities, which encode the position of each object in the ranking, where a higher utility corresponds to a higher position in the ranking. A pointwise ranking model is then trained like any other standard regression model. For example, a standard multilayer perceptron regressor could be used here, which penalizes deviations of the predicted utilities from the target utilities, using something like a standard mean squared error loss, for example. This type of ranking model has two main properties. First, it is always transitive, so if it predicts that A is preferred over B and B is preferred over C, it will necessarily also always predict that A is preferred over C. Secondly, antisymmetry, which just means that if the model predicts that A is preferred over B, it will not at the same time also predict that B is preferred over A. Both of these properties are of course directly inherited from the ordering relation on the real number line. The problem with this approach is that we don't actually optimize for the problem we want to solve, namely a ranking problem. The object B, for example, has the highest loss associated to it since its prediction is the furthest off from the target utility assigned to it. The objects A and C, however, are much closer to their corresponding target predictions and therefore induce a much smaller regression loss. This is, however, incompatible with the ranking problem we actually want to solve, since the objects A and C are actually in the wrong order in the final predicted ranking. This problem is overcome by the so-called pairwise ranking approaches. One of these ranking models is called direct ranker, which is a generalization of the maybe more well-known RankNet architecture. At first glance, direct ranker actually looks very similar to the pointwise regression approach we just discussed, in that it also maps all our objects to numerical utility value. The main difference lies in the loss function that is used to train this model. Here, the targets that are used to compute the loss are ordered pairs of objects, with the goal being to minimize the number of pairs which are ranked incorrectly by the model. The incurred loss for these two pairs, for example, would be close to 0, since the predicted utility for B is smaller than that of A and C. Looking at the first pair, however, we see that the model predicts that A is ranked over C, which is in conflict with this target, which means that this pair would incur the largest loss. In practice, one typically uses the logistic loss applied to the difference between the predicted utilities of pairs. Unlike the pointwise models we saw before, this strategy directly penalizes ranking errors and is therefore much closer to the problem we actually want to solve. Since the rankings produced by a direct ranker model are still based on predicted utility values, we again inherit the transitivity and antisymmetry from the order relation of the real number lane. Depending on the domain we are working with, having a model which guarantees transitivity and antisymmetry might be desirable, but in some domains this can actually be too restrictive. Humans, for example, don't always have transitive preferences. In such domains, one might actually find cyclic, non-transitive preferences. In order to learn such things, one might therefore need more flexible ranking models, such as the so-called comparative neural network approach. Just like direct ranker, the CMP-NN model is trained using ordered object pairs, but unlike direct ranker, it does not map the given objects to numerical utilities. Instead, it acts like a binary classifier by taking in pairs of objects and making the binary decision whether the first object is preferred over the second or the second over the first. Since CMP-NNs are thereby essentially just normal binary classifiers, they can be trained using a standard cross-entropy loss. This approach also directly penalizes ranking errors, just like direct ranker. It does, however, also allow for non-transitive preferences to be learned. The only guarantee CMP-NN still makes is that if it predicts A over B, it will not at the same time also predict B over A. This final guarantee or restriction, however one wants to look at it, can be removed by going to our last type of ranking models, the listwise ones. As the name suggests, a listwise model is trained using complete ordered lists of objects. One application where such listwise approaches might be interesting is when considering context-dependent preferences. So, for example, a preference relation where A is preferred over B when it is compared in the context of D, but the other way around when compared in the context of C. Since such scenarios are already fairly specific, we will not consider them for the rest of this talk. Instead, let us now go back to this general RankGNN architecture overview. One further remark I want to make is that in the following, when I talk about RankGNN, what I specifically mean is the combination of a graph neural network with a pairwise ranking model. Since the combination of a GNN with a pointwise ranking model is essentially just a standard GNN regressor, I won't refer to that as a RankGNN to differentiate the two. Okay, now that we have seen how a RankGNN model works, let's get into the experiments. To evaluate RankGNNs, we use a set of 5 benchmark datasets, which all consist of graphs with given target utility values. For the GNN component of our architecture, we use 3 different types of convolutions. All 3 are spatial convolutions, 2 simple neighborhood aggregation based ones and 1 higher order one. For the ranking model component, we evaluate 4 different variants, 2 pointwise models and 2 pairwise models. The pointwise utility regression model is trained directly on the target utilities in our datasets. The rank regression model is a pointwise regression model where the targets are the numerical ranks of our graphs. And as pairwise models, we use the direct ranker and the CMP-NN architectures we just discussed. To evaluate the quality of a predicted ranking, we use Kendall's tau rank correlation coefficient, which essentially just counts the number of concordant, which means correctly ordered, and discordant, which means incorrectly ordered pairs. A tau value of +1 indicates a perfect ranking. A tau coefficient of -1 would indicate an inverse ranking. With that out of the way, let's now take a look at the experimental numbers. And since this is a bit much to parse, allow me to trim it down a bit to make a few general remarks. The key takeaway from our experiments is that the pairwise RankGNN models either significantly outperform or, in the worst case, at least match the performance of the pointwise ranking models. Therefore, our experiments indicate that RankGNN models are a good choice to solve graph ranking problems. The only downside of RankGNNs compared to a simple GNN regression model we found was that depending on the number of ordered pairs one uses to train the pairwise RankGNN model, the training can be quite a bit slower than training a GNN regressor. However, since the number of sampled pairs can be easily adjusted to dataset size and hardware constraints, we don't find this to be a major problem. Now, to get a better understanding as to why these pairwise approaches apparently perform so much better than the pointwise regression approaches, let's take a closer look at the utility functions that are actually learned by them. What you see here in black is the original target utility, which was used to train the simple utility regression model, which is shown here in blue. In gray, you see the pointwise rank regression model, which was trained directly on the target ranks. And lastly, the red direct ranker curve here shows the utility values that were learned implicitly based on the ordered pair preferences it was trained with. Now, to illustrate an interesting point, let us take a closer look at this chart on the right. There we see that both for the low ranks as well as the high ranks, the target utility curve rises and falls notably steeper than for the middle ranks. Interestingly, the blue utility regression model appears to ignore these drop-offs as outliers and therefore fails to rank the objects at the beginning and the end of the ranking correctly. At least visually, both the rank regression as well as the direct ranker model don't appear to have this problem. Let's compare this with the Kendall's tau values from the table we saw before. What we find is that the blue utility regression model does have a significantly lower Kendall's tau correlation than both the rank regression and the direct ranker model. Also note that the standard deviation for the direct ranker model is the lowest of all the evaluated model, indicating that it performed most consistently across repeated runs. For a more detailed discussion of our evaluation, I'd like to refer you to our paper. Okay, let me now summarize what we talked about. We started off by describing the problem of ranking structured objects and saw that it has interesting applications ranging from biology and chemistry to the social sciences and task planning and scheduling. Then we went on and saw how the combination of graph neural networks and neural ranking models, which we call the RankGNN architecture, can be used to solve such ranking problems. In our evaluation, we just saw that the pairwise RankGNN architecture generally outperforms the simpler pointwise GNN regression approach. Lastly, let us now take a look where one could go from here. Firstly, we found that currently there aren't really any real-world graph ranking datasets out there, which is the reason why we had to resort to reusing existing graph regression datasets as ranking datasets. For future research, we therefore believe that it is crucial to create proper graph ranking datasets, since right now we don't have, for example, any data based on non-transitive or non-antisymmetric preference relations. Secondly, assuming suitable datasets are available, we believe that it would be interesting to also look at list-wise RankGNN models. Thirdly, we believe that another interesting direction could be the combination of ranking and regression. Fourth, we believe that a combination of graph kernels and ranking models such as RankSVM would also be interesting for future research. Lastly, for future work, it would be interesting to consider a much tighter integration of graph neural networks with ranking models, which may not even need the intermediary step of a graph vector embedding. For example, by constructing a special ranking convolution operator, which directly operates on pairs of graphs instead of individual graphs as it does right now. And with that outlook, I'd like to thank you all very much for your attention. I look forward to an interesting discussion.